are now on subtopic 19.6, energy transfer mechanism in thermal processes. Okay, in this section, we explore more details about heat as a means of energy transfer and two other energy transfer methods often related to temperature changes, which is convection. This is a form of matter transfer. Okay, and electromagnetic radiation, or we put it as symbol of TER if you still remember in terms of energy conservation formula in chapter 8 from physics 1. Let's begin with thermal conduction. Is the process of energy transfer by heat. Okay, can be also called as conduction or thermal conduction. Right. In this process, the transfer of can be represented by atomic scale as exchange of kinetic energy between microscopic particles, the molecules, atom and free electron, in which less energetic particles gain energy in collision with more energetic particles. For example, if you hold one end of a long metal bar and insert the other end into a flame, let's see, you have one long metal bar, okay, and you hold it here, right? Okay, in this process, you will find that the temperature of the metal bar in your hand here soon increases. Okay, the energy reach your hand by means of the conductions. Initially, before the rod is inserted into the flame here, the microscopic particle in the metal are vibrating, any part of it, vibrating about their equilibrium position. As the flame raises the temperature of the rod at this section, the particle nears the flame begins to vibrate with greater and greater amplitude because of the extra heat transferred into the atoms. These particles, in return, collide with their neighbors and transfer some of their energy in the collision. Slowly, the amplitude of the vibration of metal atoms and electrons further and further from the flame increase until eventually those in the metal near to your hand, okay, are affected. This increased vibration is detected by an increase in the temperature of the metal and your potentially burned hand. The rate of thermal conduction through a material depends on the properties of the material itself. For example, it is possible to hold a piece of asbestos in a flame indefinitely, which implies that very little energy is conducted through the asbestos. In general, metals are good thermal conductors, and materials such as asbestos, cork, paper, and fiberglass are poor conductors. Gases also are poor conductors because the separation distance between the particles is so great. The metal are good thermal conductors because they contain large number of electrons that are freely moved. Metal can transport energy over large distance. Therefore, in a good conductor such copper, conduction takes place by means of both the vibration of atom and the motion of the free electron. Conduction only occurs if there is a difference between two parts of the conducting medium. For this example, this area will be high temperature and the metal here within your hand, okay, is at low temperature. So the heat, okay, the thermal going to be transferred from hot area here to the cold area here due to the temperature difference, or we call it gradient. Okay. So this is asbestos that Madam talking just now. Okay, this is a poor conductor, a good insulator. Right. So thermal conduction, the formula of it, okay, let's say we consider this is the material, okay, having two different temperature. This area, this side is experiencing hot, okay, T hot, and this area or section is experiencing T cold. Alright, so we know there is a difference between T hot and T cold. T hot is bigger than T cold, so there is a temperature gradient, right? Thermal gradient. So the heat, the energy can be transferred from hot surface to the cold surface, passing through L, thickness of the material, where the material having A of the cross section. So the rate of energy being transferred, Q, is equivalent to Ka delta T over delta X. Okay, where K is the thermal conductivity, right, of the material. Delta X here is the L for this diagram. Right, so if we're talking about the rate of transfer of energy, Q over delta T is equivalent to Ka delta T temperature difference or gradient over the distance travel, which is the L, the thickness of the material or slab here. Right, and Q over delta T is actually power, because power is defined as rate of transfer of energy. Right, so if we're talking about power, okay, it has to be positive amount. It doesn't matter transfer in or out, but when talking about power, okay, its magnitude only we are concerned about. That is why we put modulus here. Okay, but if we're talking about heat, okay, the negative and positive does give the meaning. For positive, it means that the Q or heat is transferred into. If it is negative, it means that the Q is transferred out or taken out. So the thermal conductivity table, you have here a substance, okay, and the thermal conductivity of it. You may refer to this table later on. Continuation of thermal conduction, okay, dt over dx just now is actually th minus tc over L, right? So if we refer to this diagram, let's say you have hot reservoir and cold reservoir, okay, where the energy is going to be transferred from this hot reservoir to the cold reservoir, and the system here is insulated. The rate of transfer of energy is equivalent to Ka T hot minus Tc T cold over the length, okay, that the energy being transferred. Suppose a long uniform rod of length L, okay, is thermally insulated by insulation system here, so the energy cannot escape by heat from its surface except at the end of it, okay, as shown in this figure. One end is in thermally contact with an energy receiver at temperature T cold, and the other end is thermally contact with a receiver at temperature of T hot, where the T hot is bigger than T cold. When a steady state has been reached, the temperature at each point along the road is constant in time. In this case, we assume K is not a function of temperature. The temperature gradient is the same everywhere along the road, and consequent of it, okay, modulus of dt over dx is equivalent to th minus dc over L. Therefore, the rate of energy transfer by conduction through the road is equivalent to KATH minus TC over L. Okay, for a compound slab containing several material of thickness L, okay, let's say we have few material combined. We have L1, L2, and so on, with different K1, K2, and so on. The rate of energy transfer through the slab at steady state is equivalent to ATH minus TC over sum of, okay, sum of Li over Ki, okay, of the material. Okay, you can imagine that, okay, K is put it down here, okay, over K and over K here, right? So that is how we manage to get this. Quick quiz 19.5. You have two rods of the same length and diameter, but they are formed from different materials. The rods are used to connect two regions at different temperatures so that energy transferred through the rods by heat. They can be connected in series as the top figure here, or in parallel as the bottom figure here. In which case is the rate of energy transfer by heat larger? Right, so this quick quiz is going to be your task. Okay, once you finish watching this video, submit it into Google Classroom. Example 19.7, energy transfer through two slabs of thickness L1 and L2, and thermally conductivities of K1 and K2 are in thermal contact with each other, as shown in this figure. The temperature of either outer surface are Tc, right, and Th respectively, and Th is bigger than Tc. Determine the temperature at the interface at the rate of energy transfer and the rate of energy transfer by conduction through an area A of the slabs in the steady state conditions. So we have P1 is equivalent to K1A T minus Tc, right? This is for slab number 1 here, right? So what is the T? T is in the middle surface, the contact surface. Okay, and then P2 is equivalent to K2ATH minus T in the middle here over L2. So this must be the same because the rate of transfer of energy from slab 2 must equivalent to the rate of transfer of energy to slab 1. So P2 is equivalent to P1. So you equate these two, then you will get rearrangement to be done so that you can solve for unknown is your T. Okay, so this is for your T, and this is the rate of transfer within this surface, P. Suppose you are building an insulated container with 2 layers of insulation and the rate of energy transfer turns out to be too high. You have enough room to increase the thickness of one of the 2 layers by 20%. How would you decide which layer to choose? Based on this formula that we already determined in previous part, to decrease the power as much as possible, you must increase the denominator of this equation as much as possible, isn't it? Right. Whichever thickness you choose to increase, whether L1 or L2, okay, you increase the corresponding term of L over K. It means K, which is in the denominator, by 20%. For this percentage change to represent the large absolute change, you want to take 20% of the larger terms. Therefore, you should increase the thickness of the layer that has the larger value of the L over K. That is how to deal with this one. Right, home insulation. In engineering practice, the term of L over K here, okay, for a particular substance is referred to as R value, right, of the material. So now this equation can be rewrite in terms of, instead of putting L over K, we can have R symbol here, okay, because R is L over K. The R value for few common building materials are given in table 19.4 here. Okay, in US, okay, the insulating properties of materials used in buildings are usually expressed in US customary system or units. Okay, therefore it has feet square dot degree Fahrenheit dot hour over BTU, British thermal unit, right? Not as in SI unit, right? So you might need to convert this value. Okay, we'll see in one of the example. Example 19.8, the R value of a typical wall. Calculate the total R value for a wall constructed as shown in the figure. Starting outside of the house towards the front in the figure and moving inward, the wall consists of 4 inch of brick, 0.5 inch of sheathing, and airspace 3.5 inch thick and 0.5 inch of drywall. So this is the constructed wall. Okay, given to us, okay, the R1 outside stagnant air layer is this amount. The brick as R2 is this amount. You must refer to table given, previous table. R3 is the sheathing, this amount of it. R4 is airspace, okay, this amount of it. Drywall as for R5, and R6 is inside stagnant air layer. So the R total for this wall going to be R1 plus up to R6, which gives you this value of R total. Suppose you are not happy with this total R value of the wall. You cannot change the overall structure, but you can fill the air space as in the figure, okay, with insulation. To maximize the total R value, what material should you choose to fill the air space? Okay, so looking at figure or table 19.4, we see that 3.5 inch of fiberglass insulation is more than 10 times as effective as 3.5 inch of air. Therefore, we should fill the air space here, okay, with the fiberglass insulation. The result is that we add up 10.90 feet square dot Fahrenheit dot hour over BTU of R value, and we lose 1.101 feet square dot Fahrenheit dot hour, okay, over BTU due to the airspace that we have replaced with the insulation of the fiberglass material. The new total R value will be, okay, 7.12, okay, feet square dot F dot hour over BTU plus 9.89 feet square dot F dot hour over BTU. Okay, that gives us, as the R total right now is 17.01. We actually fiberglass is 10.9. However, it becomes like this because we have to minus the air layer that we take out, because we fill up this area with the fiberglass. So the R6 here become this value. Okay, so this is your R total. Okay, now convection. Okay, energy transfer by movement of a warm substance is said to have been transferred by convection. Right, which is a form of matter transfer. So this is a kind of TMT, or transfer of matter transfer, in equation 8.2, or conservation of energy. When resulting from differences in density, as with air in the toaster here, right, the process is referred to as natural convection. If we place our bread, we want to warm up our bread, we put our bread or croissant on the top here, right? So what happen is the warmer air coming from the toaster going to move up and warm our bread or croissant. Okay, when resulting from differences in density, as with air in the toaster just now, this kind of process is referred as natural convection. Airflow at an ocean coast, okay, is an example of natural convection, as the mixing that occurs as surface water in a lake cools and sink. Okay, as we discussed in section 18.4, when the heated substance is forced to move by a fan or pump, as in some hot air and hot water heating system, the process is called forced convection. So in convection, we have two types: natural as usual, due to the movement of the air due to the change in density of it. But for forced convection, okay, the movement, the flow of the material substance due to the pump or fan, external agent. Okay, so that what we call forced convection. Next one is radiation. This is the third means of the energy transfer, we shall discuss in electromagnetic radiation. Okay, all object radiates energy continuously in form of electromagnetic wave. Okay, this one is obvious, but even from our body, okay, also we have a radiation, okay, transmitted all over our body throughout the time, okay, non-stop until we die. Okay, this is due to the radiation here, okay, is produced by thermal vibration of the molecules within the object. Okay, we are familiar with electromagnetic radiation in the form of orange glow like this, okay, from electric stove burner or electric space heater. In toaster, as mentioned in the section on convection just now, energy reached the bread by electromagnetic radiation from the glowing coils, which you can see if you look downward into the toaster. The rate at which the surface of the object radiates energy is proportional to the fourth power of the absolute temperature of the surface, known as Stephen's law. Okay, in terms of equation, this is the rate of energy being radiated by Stephen's law. So P is the power, okay, in unit watt, all right, and sigma is the 5 sigma value is equivalent to 5.6696 times 10 to the power of -8 watt per meter square dot Kelvin power 4. A is the area of the surface, E is the emissivity, and T is the temperature, surface temperature in Kelvin. The value of E can be varied from 0 up to 1, depending on the properties of the surface. The emissivity here is equivalent to the absorptivity, which is the fraction of the incoming radiation that the surface absorbs. A mirror has a very low absorptivity because it reflects almost all incident light on it. Okay, therefore a mirror surface also has a very low emissivity. Okay, at the other extreme, a black surface has high absorptivity and high emissivity. An ideal absorber is defined as an object that absorbs all energy incident on it. And for such an object, E is equivalent to 1. This is for ideal absorber, known as black body. We cannot see the object because the object absorbs all the lights, okay, that falls on the surface of it. That is why we call it ideal absorber. That is why the object known as black body. Right. Alright. As an object radiates energy at a rate given by equation Stephen's law just now, okay, it's also absorbed electromagnetic radiation from the surrounding, okay, which consists of other objects that radiate energy as well. If the latter process did not occur, an object would eventually radiate all its energy, and its temperature would reach absolute zero because it's going to transfer out all the energy, okay, by the electromagnetic radiation. If an object is at a temperature T and its surroundings are at an average temperature of T0, the net rate of the energy gain or loss, okay, by the object as a result of radiation is P net equivalent to sigma A E T power 4 minus T0 power 4. T is the temperature of the object. T0 is the temperature of the surrounding of the object. E is the emissivity of the object. A is the cross-section. Sigma is a constant. Okay. When an object is in equilibrium with the surrounding, it radiates and absorbs energy at the same rate and its temperature remains constant. When an object is hotter than its surrounding, it radiates more energy than it's absorbed, okay, and its temperature decreases. One of the best mechanisms that people figure out is about the Dewar flask. Okay, so the Dewar flask is a container designed to minimize the energy transfer by the conduction, convection, and radiation. Such a container is used to store cold or hot liquids for long periods of time. Okay, an insulated bottle such as thermos is a common household equivalent of a Dewar flask. The standard construction, which is this figure shown here, consists of double wall pirate glass, silvered wall, okay, and then there is a space between the wall. The space between the wall is evacuated to minimize the energy transfer by conduction and convection. So there is no air molecule at all, supposedly, in this area to reduce the transfer of energy in terms of conduction and convection. The silvered surface, okay, minimize energy transfer by radiation because silver is a very good reflector and very low emissivity. A further reduction is energy loss is obtained by reducing the size of the neck here. Dual flasks are commonly used to store liquid nitrogen with boiling point at 77 Kelvin and liquid oxygen where the boiling point is 90 Kelvin. Okay, to confine liquid helium where boiling point is 4.2 Kelvin, which has a very low heat of vaporization, it is often necessary to use a double dual system in which the dual flask containing the liquid is surrounded by another or second dual flask. The space between the two flasks is filled with liquid nitrogen. Right. The newer design of storage container are using super insulation that consists of many layers of reflecting materials separated by fiberglass. This is even way better. All this material is in a vacuum and no liquid nitrogen is needed with this newer design. Okay. So we have finished this chapter, and then this is your task number 2. You need to explain the problem in the cooking process in the storyline. Okay, from your textbook. Okay, the opening of this topic. Okay, where the problem involving the boiled eggs, hamburgers, cookies, and cakes. So you need to explain what happened, why is it happen, so what's the problem, okay, and submit all this explanation into Google Classroom. Thank you. Assalamualaikum.